Hello, everybody. What I'd like to do today is talk about implementing a stack using linked elements. So I'll start off by reviewing some of the material that we had already talked about before during our previous lecture, and then I will continue on discussing the new material in the remainder of this set of slides. As a summary, we have seen that arrays could be used as an efficient way to implement different kinds of data structures like stacks and so on. There are other data structures that could be implemented using arrays also, like queues, etc. Accessing any elements of arrays will involve a certain constant number of operations. It's a random access type of a container for data, so we can jump around the different indices inside the array as we please. But however, there were drawbacks associated with using arrays for implementing data structures, which more or less includes one, the amount of physical space that we have to allocate. If we're using array implementations for data structures, we typically have to accommodate for worst case scenarios with regards to the size of the data structures that we are building. So for example, as I had mentioned before, if you have a data structure that will accommodate 0.01% of the time 100,000 elements, but in the remainder of the time it will accommodate only 50 elements, you have to in the general implementation create an array size that will accommodate the worst case scenario as such. Generally, array implementations are typically slower when we have to resize those arrays to accommodate more elements. That will certainly involve creating a new array, copying elements from the previous array into the new array, and then updating the references accordingly. And this certainly involves a lot of time associated with an operation like expanding an array size, or even contracting an array size, and so on. So linked lists prove to be very useful and foundational data structures for being able to use them to build other kinds of data structures like stacks and queues and trees and graphs and so on and so forth. So creating a linked list basically is very foundational. We'd like to learn how we can create a linked list, how we can insert elements into the linked list, how we can delete elements, how we can traverse elements in the linked list, and so on. The nice thing about a linked list is that it is composed of nodes, and we can jump across the various nodes or traverse from one node to another, as you can see in the structure in front of you. So we can start off by what is called a head, and then start propagating the different nodes until we reach the terminal node, which is typically designated by a certain value for its next pointer, as we had seen before. Accessing the first element using linked lists will be very fast, but accessing any subsequent elements will really necessitate traversing the data structure one node after another in order for us to be able to go through the entire linked list, or even to find an element inside the linked list, and so on. Finding an element in a linked list is certainly overheadful as compared to maybe accessing an element inside an array using an index right away. Just like arrays, each element in the linked list has one single predecessor and one single successor. Except for the first and last elements, we label this data structure as being a linear data structure. Linked lists need not necessarily be implemented with contiguous memory locations. So as we implement linked lists, we don't need to have the various elements composing the linked list beside each other inside memory, like we have to have in most array implementations. So how do we really implement such kind of a structure in Java? And iterating on what we had seen before, we're going to basically create or define what is called a node. That node will be composed of a payload as well as a pointer to the next node inside the data structure. In the specific example in front of us, we have a node that is modeled using a class called LM. It has a value inside it, which is really a reference to an object that will hold the payload, and we also have a reference pointing to the next node inside the data structure. This is the public LM next. As you can see, the definition in front of you defines LM in terms of itself. So public LM next is actually defined inside the class called LM, and this is what we call a recursive definition of a node. It's an example of a recursive definition. Let's see what we can do with something like this. So if we simply create a node reference or an LM reference, and we call that P, this reference P is initialized to null, as you can see in front of you. And then what we could be doing is, once we start allocating an object of type LM, as you can see on the right hand side below, that an actual object of that node is created, what we could subsequently do beyond this is simply say P equals the new more or less allocation that had been made, and therefore the reference P is actually pointing to a node inside memory. As you can see in front of you, what we have is a reference called P that is pointing to a node of type LM inside memory. The payload of that node is initialized to null because it's a reference in itself, and the next pointer is also initialized to null. So if we want to set the value or the payload, we can simply say p.value equals an instance of a given object. And what this does is, as you can see, it simply sets the value of the reference inside the payload portion of the node to point to that new object that had been created. In this case, it's a new time object inside memory that contains the value 1300. Subsequently, let's see how we can create another node. So we're going to create a new LM. So that creates a new node whose payload is equal to null, and its next reference is equal to null also. And if we say p.next is equal to new LM, as you will see, the node in front of you that holds the value or payload 1300, or actually references the object in memory that contains 1300, the next portion of that node will point to the newly allocated object. So what you see in front of you is what looks like a linked list now that is starting to become apparent. As you see, we have a pointer P, which is really the head of the linked list that is pointing to a node whose payload contains a reference to an object that holds 1300, as well as its next that points to a newly allocated node inside memory that has a null payload and a null next pointer, or reference. Again, if we start off with the head, which is called P, and we simply say p.next.value, so p.next itself is the pointer in the first node. Actually, I'm sorry, it's a reference in the first node. There are no pointers in the Java programming language. It's actually the reference inside the first node. So p.next is that reference inside the first node, and it's actually pointing to the actual memory location of the second node inside the linked list. So if we say p.next.value, what we're doing is p.next is really referencing the second node in the linked list in front of you. .value is actually the payload portion. If we set that to new time, so we are referencing an object inside memory that contains the hour 1430. If we create another node, again, we can say new lm. As you can see, it creates a new node in front of you. If we say p.next, now this is the reference next of the second node, the one containing 1430. So if we say p.next, this is like I said, the reference in the second node that contains or references the payload 1430. So if we say that this is equal to new lm, what's happening is that now it's actually linking to the last node in the linked list in front of you. P.next, .value equals new time. Now, as you can start to see, this is a very inconvenient way of trying to access the payloads of the different nodes inside the linked list. We can't keep on going like this forever, so we can't keep on saying p.next, .value to refer to the payload portion of the last node. What if this linked list is 100 nodes in capacity? So we can't continue doing things like this. We have to find an alternative way to be able to traverse the linked list. So here p.next equals p. What this will do is it will simply have that next reference in front of you point back to the beginning of the linked list, and we just created ourselves what is called a circular linked list. There are many different kinds of linked lists. There are singly linked lists, there are doubly linked lists that have both a next and a previous reference in them. There are doubly circular linked lists that have the first node reference the last node, and the last node reference the first node again, and all those have different applications for different data structures. They impact efficiency, but again, they may impact how much memory you will be using. We just created ourselves by doing a p.next equals p. We just created ourselves a circular data structure, but you have to be careful what you or we had just done now by saying p.next is equal to p. We simply just created garbage, which is more or less the last node that shows up in front of you. So we'd like to create a linked list data structure that represents a linear data structure, such as lists, stacks, and queues. So we're going to use linked lists to be able to create other forms of data structures, like lists, like stacks, like queues. We'll start off with a very simple stack, and then we'll see implementations of queues and lists later on using linked lists as such also. The nice thing about the linked list data structure is now we can start allocating memory on demand. So if we need to add an element in the stack, we could simply create a new node, add it to the linked list, just keep track of where the top of the stack is, and then boom, we simply have ourselves a very simple stack implementation. So in summary, linked data structures are alternatives to arrays to store a collection of values. They are always use the required amount of memory because each element is stored in its own container, which is the node, what we call here LM. Each container or node is linked to its successor or predecessor in more advanced versions of linked lists with the help of reference. We're going to limit ourselves to linear data structures like lists, stacks, and queues, but we could also use linked lists to certainly represent graphs and trees. So this is a typical constructor for the class LM. So this is the node of a linked list. This is how its structure is formed. So we have ourselves an object value. This is a reference to the payload object that the node will reference. We have ourselves an LM next, so we have a reference to a node of our same kind. This is called next, so each node will be more or less pointing in memory to a successor node inside memory, and that successor node is also of type LM. The constructor, as you can see in front of you, simply takes a payload, a reference, and it takes a reference to another node, what you will be pointing to next. So as you are creating a node, you will specify what its payload would look like and what its next reference would point to, and this is exactly what is done in the constructor in front of you. So a typical usage would be like this. We can say p equals new lm, passing it the string a and null. So as you can see on the right hand side of the screen in front of you, that we have a reference p that is now pointing to an object inside memory, a node that contains a payload and contains a reference to the next node. In this specific case, it's nothing. If we say q equals new lm b and p, so now we have a new node that is created that contains the payload b in specific. I'm just saying that in short, the payload b, but it's actually again a reference to an object in memory that contains b. It contains the payload b, and its next reference is pointing to what p points to. So you know, the figure in front of you on the right hand side of the bottom of the window shows exactly what this refers to. So we can easily fall into pitfalls by manipulating nodes as such. In the example in front of you that we had already seen last time, we're creating an lmp equals null. So we have ourselves a reference to a node that is initialized to null, another one called q that is initialized to null. We are creating one single node and storing inside it the value 1, and its next reference is pointing to nothing, this is going to be pointed to by p. But now if you notice, q, that reference is null. It does not point or reference an object inside memory, and if we try to simply say q.next, there is no object inside memory that contains a next attribute inside it, so therefore we will immediately be getting a null pointer exception. So this is the diagram that illustrates the problem. Again, the intent was to probably create a linked list so that q.next will designate the element currently designated by p. So the appropriate statements should have been allocate a new memory and have that referenced by p, allocate a new memory and have that referenced by q, and then say q.next is equal to p. So don't forget to allocate the nodes before you actually start accessing their payload and their next reference. So one safety net is to always check that the reference is not equal to null before you actually start accessing the attributes inside the object that supposedly is referenced by this reference. This will kind of protect you a bit in terms of null pointer exceptions, but as we will see later on, we will work with exception handling, and we will see how we can kind of recover from problems like null pointer exceptions. So this is a linked implementation of a stack. We have a public class linked stack that implements stack. So the stack interface will contain 4 prototypes. It will have a prototype for an empty method, for a push that takes an object, and the objective of that is to push an object on top of the stack, a peek that more or less looks into the stack's topmost element, and actually doesn't remove that from the stack, but just simply takes a look into what its value looks like, and a pop that really removes the topmost element from the stack. What we want to do is public class linked stack implement stack. We are going to create a reference that will allow us to keep track of where the top of the stack is inside the linked list. As we had seen before, when we had created stacks using an array-based implementation, we created a variable called top that always keeps track of the index of the element in the array that is going to be the topmost element in the stack. So we had started the top of stack in the array-based implementation with a value of -1. Every time we pushed an element onto the stack, we simply incremented the top of the stack, added an element there. We want to push another element, we increment the top of the stack and add an element there, and so on and so forth. And every time we wanted to pop out of the stack, we simply took the element out from the cell location that, or the array location that was indexed by the top of the stack, and simply decremented the top of the stack, of course with due diligence that the top of the stack need not exceed the array size or actually go below what the proper and appropriate index should look like. So we have to always be careful not to exceed the array capacity and not to take an element out of the array when there is nothing inside the array, or the stack implementation in such a case. So we're going to, in this linked stack implementation, if we have ourselves a linked list that is pointed to by a head, and like I said before, it's very, very critical that you always maintain the head, that you never lose track of the head, because you may be very well creating a garbage inside memory if you lose track of the head. So always anchor your linked list with the head. And if you want to propagate around the linked list for whatever reason, you can create a runner or a cursor that basically starts from whichever location in the linked list you can access. Like in the simplest case, the trivial case, you start from head and just keep on running throughout the linked list until you find an appropriate node or do whatever functionality you wish to perform. So if we have ourselves a linked list, we will create a reference also called the top of the stack, or the top, that will allow us to keep track of where the topmost element, designating the topmost element that is of the stack, is inside the linked list. Whether we keep track of the top or keep track of the bottom, as we had seen last time, because of the nature of the stack, that we're always manipulating elements from the top of the stack, so it makes more sense to maintain a reference that really points to the topmost element of the stack inside the linked list, as opposed to maintaining a bottom, and this we had seen last time. So therefore, we'd like to start seeing an implementation of the class LM. So this is the node. Again, we're just expanding the implementation that we had seen before. We have ourselves the payload reference, which is value. We have ourselves the next reference, the reference that will be pointing to the next node. The constructor takes a reference to the payload and a reference to the next node to point to. We'd like to set the value of the payload. We'd like to set the value of the next reference. We'd like to get the value of the payload, and we'd like to get the value of the next reference. And these are just the simple getters and setters inside the LM class, which is more or less the node of the linked list. This is the class LM. Again, it has the reference to the payload and the reference to the next, and we also have the constructor. We are declaring, in this case, the attributes as being protected, and we'll see, or we had seen before, that protected could be used with inheritance, so that eventually, you know, in such a case, we can kind of control the access to the various instance variables and the methods inside. Public class linked stack implements stack. In the specific implementation in front of you, we decide to create the node as an inner class inside the linked stack implementation. So we have a couple of options here. One option is to have declared the node class outside of the linked stack. Or in this specific example in front of you, we are really declaring the node inside the linked stack implementation. So there is an advantage to declaring the LM class or the node class inside the linked stack implementation, because in this specific case, the linked stack could really see and access the constituents of the node. So without having to call functions, it could make the implementation more efficient depending on how we design it. But the linked stack does now have access to the various attributes inside and the methods inside the LM class. So it's a nested class of the class linked stack, even though the visibility of the class is private and the visibility of its instance variables are private. The linked stack does still have access to the instance variables of LM because it is a nested class inside the linked stack. So we're going to use generics as we had seen before. So public class linked stack implement stack. We'd like to be able to use generics here so that we can create a more flexible implementation of the linked stack, as we will see. So again, we will be keeping track of the top most element inside the stack. So a reference to a specific node inside the linked stack will tell us where the topmost element inside the stack will be. So we're going to attempt to now perform an implementation of the constructor, the isEmpty method, the peek method, and the pop method, and also the push method. So peek, what peek would do, as you can see in front of you, this is a linked list that starts off with a head reference called top that we just decided to call top in this specific implementation. This will be the reference that always points to the topmost element inside our stack. So at any point in time, if I want to eventually push an element onto the stack modeled by this linked list, we will actually have it in between, actually right before the 3, and have top point to that accordingly. In the specific example in front of you, if we simply want to pop an element out of the stack that is modeled by this linked list, then we will simply remove the element that is pointed to by the top reference, in this case, which is the node that contains the payload 3. A peek operation should really give us back the value 3 without actually removing that node from the linked list. How do we really, as another subproblem, how do we detect the end of a linked structure? So in the above picture, as you can see, we have ourselves a head of the linked list, and that is called P. And there are 3 nodes, one that contains a payload 1300, another that contains a payload 1430, and a third that contains a payload 1600. How do we really detect the end of the linked structure? As you can see, by virtue of design, the last node in the linked list has a next reference that is equal to null. So if we want to simply traverse the linked list, all we can simply do is just start creating a cursor or a runner reference that starts at P, and what we could be doing is simply it starts out points to the first node in the linked list, and something as simple as while the cursor dot next is not equal to null, which means that there is a next node to traverse, we can simply have that cursor jump to the next node, so we can say the cursor is equal to the cursor dot next. So again, while the cursor, which starts at P in this specific case, while the cursor dot next is not equal to null, which means that as long as there is something else to traverse, jump to that. So we can say cursor equals cursor dot next. So the traversal, let's take a look at a very small example to simply override the method toString so that we can print the contents or traverse the contents of an entire linked list and print its contents. So this is the public string toString. We are overriding this method. We're just starting off by printing a square bracket. If the size of the linked list is greater than 0, we want to just create a counter called P that is initialized to 0. The resulting string that we will be giving back, this is actually a traversal of an array-based implementation of a stack. So again, we're starting with a string that we will give back that's called result, and this is initialized to the square bracket. If the size of the array is greater than 0, then we're going to start a counter that is equal to 0. We're going to append to the string result the array location P, or the content of the array location at P. Simply increment the value of the counter, so make P equals to P plus 1, and then simply say while the P is less than size, while the counter is less than size, so while there is something still to traverse, just continue appending the elements of the array to the resulting string, increment the counter, and once you're done, simply return the result. What if we want to do this for a linked list implementation? So we'd like to complete the above. How are we going to do this? So that's a very simple exercise. As I said before, what test can we do or perform to check whether the stack is empty? Again, if the top or the head of the stack or the head of the linked list, more or less, or the top reference now is equal to null, this is an indication that there's absolutely nothing inside the linked list, so we could add this. This is an indication that the list is not empty, so we can simply say if the top is not equal to null, what do we want to do in such a case? We want to simply start creating or getting an element inside the linked list. So we are going to say element P, this is a node reference, and this node reference is going to be initialized to the top of the string, the linked list, as you can see in front of you. So this is going to be our runner, or the cursor that I had mentioned before. So we are initializing a runner or a cursor that we call P here to the first node in the linked list. So lmp equals top, so it's reset to the beginning of the linked list. We are going to do the exact same thing, simply extract the content of the payload. So we're going to say the result is equal to the result plus the payload of the node pointed to by P. Then we simply want to advance P, so we are going to say P equals P arrow next, and this is what is going to happen. So P is going to equal P dot next. I said arrow next here. I was just going back to my C++ skills, but again, one more time, we're simply saying P equals P dot next. This is how we advance the reference to the subsequent node as such. Then we want to check whether there is something to continue traversing or not. So while the runner or the cursor, what we call P, is not equal to null, we are going to continue appending the values to the result, continue making P equals P dot next until eventually we hit a value of the runner that is equal to null, so that stops the while loop. And in such case, we have ourselves more or less a resulting string that contains all the payloads inside the linked list. You just have to make sure that the payload is appended properly to the string. As you will notice here, our payload is actually a reference to a node inside the linked list. So this is what had happened. We started at the first node, we continued to the next node, concatenating the value of the payload, the subsequent one, and then eventually p arrow next or p dot next will equal to null, and this is when we will know when to stop. So what is the problem with, or the commonly occurring mistake with the above? So as you can see here, in this specific code, if we had not used a runner or a cursor to run through the linked list, and we simply had manipulated the head of the linked list, or what we call here top. As I mentioned before, it's very critical for you to always anchor the linked list with the head. Never lose track of the head reference. Simply what happened here, if we simply manipulate top, so top is pointing to the first node, top equals stop.next, you immediately created garbage, more garbage, subsequent garbage, and then you just lost your entire linked list. So never please manipulate or run through the linked list using the head reference. Again, never run through the linked list using the head reference. Always make it a point to create yourself a runner or a cursor, a reference that will run through the linked list on an as-needed basis. So what we had seen today is an alternate implementation of a stack using a linked list. Linked lists are advantageous because they can allow you to allocate memory on an as-needed basis. They do have some disadvantages also in terms of runtime performance, but then at the end of the day, these are very, very critical and important implementations that we have to know of. And thank you very much.